So next we have a talk on Fram, a new language aiming to increase the ergonomics of algebraic effect handlers. And over to Piotr, once the screen's ready.
Can I move this down? Okay, so thank you for your introduction. This is joint work with Patrycja Balik. Patrycja is there. I will start with something completely different. So in 1879, USS Jeannette sailed through the Bering Strait and got stuck in the ice. And after almost 2 years of random drifting, the ship was crushed by the pressure of ice and finally sank. But the remains of the ship were found near the Greenland, so this inspired Nansen to organize a journey to the North Pole. His idea was quite simple: just get stuck in the ice and wait. But he needed a ship that would withstand the high pressure of ice. So they built a ship called Fram. Fram in Norwegian means forward, and they tried to reach the North Pole. However, they didn't manage to, because the random drifting of ice, they go in wrong direction. However, the ship was used in another polar expedition, in the well-known Amundsen expedition to the South Pole. So we decided to name our programming language after that ship. And our initial goal was to improve ergonomics of programming with algebraic effects and especially lexically-scoped effect handlers. However, we tried to experimenting with some implicit parameters, and we started to generalize this mechanism, and we finally realized that it's quite interesting thing, which is not related to algebraic effects. So today I will say absolutely nothing about algebraic effects. So, let's start with the beginning. Fram is designed in the tradition of ML, so like many other ML programming languages, its type system is stratified between types and type schemes. The idea is that types describes expressions and type schemes are polymorphic, but they can describe only variables. So each time when we use a variable, it must be immediately instantiated with some types. So this is not the full system F, it's something weaker, but still is very expressive and have decidible type inference. And this stratification allows for many useful extensions. For instance, we have rank and types. In rank and types, we observe that parameters of functions are usually bound by variables. Variables can be polymorphic, so functions can take polymorphic arguments. Another well-known extension is known from Haskell. We can have type classes. We just introduce a new construct to the type schemes and the class constraints. So each time when we use a variable, we have to find appropriate class constraints, or at least propagate them to the place where it can be abstracted. In Fram, we followed this approach, and the grammar of types look like this. We have types, type schemes. Types are just arrows, effectful arrows, and other things. And schemes have very uniform shape. Schemes abstract over some named parameters, and these named parameters can be just types, anonymous types, or named types, or named parameters, or optional parameters, implicit parameters, and some other things that I will not talk about today. For type parameters, when we write an identity function, it's a well-known polymorphic functions. It's in Fram, its type or type schemes looks like this. It's a just function which takes some anonymous type and some value of this type and return its value, this value. So we can write identity function like this. It's the same as in Occam. We can write it like this. So we can explicitly abstract over these anonymous types. And it behaves like exactly like locally abstract types in Occam. It's just, we name the type which is named locally, but on the outside it's still anonymous. But we can use named types here. And the difference is that this type now is named. The name is part of its scheme, type scheme, so we can explicitly instantiate such a function. We can call ID3 and say, okay, I'm using ID3 with type t equal to int. So we obtain an identity function on integers. And now implicit parameters. So our original motivation was something like this. Let's assume that we want to compute something. And it's a quite big computation, so we need to compute this and compute that. And so we have a lot of code that do something, and now we want to change it. We want to add some logging. So we create some capability of logging, some object that will be used for logging for logging to file, and we need to pass somehow this object to the place where it's used. The obvious way to do that is just to pass it as another parameter to each functions, but it's a very bad design. We need to pollute the code with some boring parameter passing. So we followed the approach to implicit parameters by Lewis and others, where we have a separate namespace for implicit parameters, and each time where function expects such implicit parameters, we are looking for such a parameter in the environment, resolving it by name. So now we don't need to pass it explicitly, but still we bound it explicitly in functions. Such implicit parameters are implemented in Haskell, and in Haskell they also are abstracted implicitly, the same as class constraints, but such a design is good for Haskell, where programmers usually write type annotations for functions, for top-level functions, and in each function they say explicitly which implicit parameters they expect. So, but if we only rely on the type inference, it's very error-prone. When we do some typo in the name, then we got an error, and it's hard to figure out where this error comes from. So we observed that definitions that share some implicit parameters usually come in some groups. So we inspired by Coq, the section mechanism in Coq, we introduce a new construct called implicit. It's a like variable in Coq. We say, okay, we will use this log implicit parameter in the following functions, and each time when it's used, it means that this function must abstract this implicit parameters. So now values, function that takes values. Implicit parameters are values, now are part of the scheme. Schemes can abstract over some values, and these values can be instantiated explicitly. We can say, okay, we can compute that function from the previous slides, saying, I will use the standard error for logging, or we can omit this parameter, and then it's resolved by name. But we can have different policies for resolving such omitted named parameters for different kinds of named parameters. We can have optional parameters, and when it's omitted, then we take some default values. We can have usual named parameters, which cannot be omitted. So everything now is very simple. There are very simple ideas. So now we will do the complex things using very simple methods. Usually we do the opposite direction. So let's start with records. In many programming languages, we have special kind of data types called records, and records are just tuples where components are named. In Fram, we have no records. Records are just syntactic sugar. So such a definition in Fram is desugared for that. It's an algebraic data type with single constructor with the same name as the type. And this constructor, it's polymorphic. It's polymorphic in these named parameters, because these named parameters are part of the type scheme. So we say it's polymorphic. And also, Fram, for such records, generates some methods that allows to access each field of this record. So with this definition, so we just write the line as on the top of the slide. It's desugared to these 3 lines, and now we can write code like this. Just, okay, let's compute a sum of two records, 2 vectors. So we create new vectors and can access each component just by saying .x, .y, and everything's for free. Another thing, existential types. So let's start with this simple example. Here we have church encoding of streams. So what's the stream? Stream has some existential type called st here, which represents some hidden state of the stream. We have the current state and a function that produces next state and the next element. So we can iterate this function to produce other elements of the stream. So let's try to write some code that operates on stream. So we will write map I function, which is usual map function, where this parameter f is a function that takes not only element but its index in the stream. So this function, so we need to produce a new stream. So the new stream will be a stream. The current state now can be different. Its stream contains some abstract type, so we can choose type that we will use. So we will use a pair of current index and the state of the current state from the previous stream. And we have this function that produces next state and next element, which is quite obvious. But now, if we want to explicitly say that this new stream This abstract type st in this new stream is a pair. We can write like this, of course. But how to access, what we should write in the place of this underscore? For this underscore, we need to write a type st from the input stream. I don't know how to do that in Occam, but in Fram, because this parameter is named, I can explicitly bound it here. Okay, and another example, functors, the module functors. Here we have some code in Occam. The keywords are orange, so it must be an Occam. And here we have maps, finite maps. So we have some signature which contains key, some abstract type t, empty map, adding new element to map, finding element in map. And having such a signature, we can write a functor make. I only put a signature of this functor here, which takes keys. Keys are just type with comparator. And we produce a map where this type key is the key that we taken as a parameter. And we can call this functor just providing some module. So let's try to rewrite this code into Fram without using modules. Or we have modules, but we have no module functors. So let's try to write it. First, the module signature can be just a algebraic data type, which have several named parameters. The only constructor map have several named parameters. It has some existential type t, and empty map, adding, finding, and other operators. So what's a module functor? It's a just usual function which takes type with comparator and returns a map, element of that input stream. So far, everything is quite simple. We can do the same things in Occam, and it's a well-known translation of generative functors to some simpler system. But what we should do with this module application in Fram, we can call this function make, and saying, OK, let's take every named parameter that this function expects from the module int, just by resolving it by names. So if module int contains such comparator, then we will provide it to function make. And we can do the same with the result of function make. We can pattern match on this map type and say, OK, let's bind every named parameter of that constructor to the new module or namespace called intMap. So it looks like generative functors, but we don't need functors in our language. So to summarize, we developed Fram, and what's interesting in this language is that we developed it together with students. We use it in teaching. So we have classes where students talk about the design of the language. They implement something in the type checker or interpreter of that language. So it's quite interesting experience for us because they ask very rookie questions. They have different view. They know some other programming languages, and maybe they are not very fluent in the functional programming. So we got interesting feedback from casual users. The Fram is developed together with its theory. The core features of the Fram we already formalized in Coq. So we have logical relations for effect capabilities, the effect system that we have in Fram. Patrycja talked about it on Hope workshop on Monday. We also have a proof of coherence of our implicit parameters mechanism. And it's still work in progress and some experiment, but we obtain such interesting thing. It's a very simple, uniform language where it's quite expressive. We can express very complex features known from other programming languages using very simple tools. And we still work on improving ergonomics on programming with algebraic effects, but it's still work in progress. We still change the effect system a little bit, so we will see where we will go. So thank you for your attention.
Thank you, Piotr. Do we have any questions?
I think there was some sneaky stuff going on. So the module encoding was relying on the fact that T is a type constructor, not a type.
You mean you are asking for modules, yes?
Yeah.
And
so go back to the slide. Yeah, so look at that first occurrence of T. Oh,
here. Yeah.
So there's some dependency, right, between the things in the set, right? Because you name T first and then you use it later within the same recursive bindings, and also it's higher. Oh, maybe it isn't, is it? Yeah, it's T applied to val, right?
Yeah, T applied to val. The T is of higher kind. It's
okay.
From type to type.
Okay, so it's more than just
ML.
Okay, fine.
Can you say something about the effect types? Is this on? Now it's on. Can you say something about the effect type system?
So we have how to say it? Okay, we have lexically-scoped effects. So and based on effect capabilities. So each handler provides some value that can do effects. And each time when we call a handler, a new fresh effect is created. So we can track it that it will never escape, that effects will never escape their scope. And so the effects cannot be parameterized, right? They are just fresh effect variables. So it simplifies a lot in type inference. And I don't know what you want to hear about.
So is it based on some kind of row typing system, or is it more just sets of effects? I mean, what is it?
Currently, it's a very good question. Currently, we have rows, but we are going to change them to sets.
Okay.
We have some ideas how to do that, but it's still not implemented.
Thank you.
We can thank Piotr one more time. End of this first session a little bit early. See you again at, I think, 11 o'clock for session 2. Thank you.